Hello and welcome. Today, we're digging into the world of foundation engineering. We're talking about the incredible, totally invisible structures that hold up, well, everything from our homes to the tallest skyscrapers. So yeah, let's get into it. I mean, seriously, have you ever really thought about it? You see some massive tower reaching for the clouds, and you just assume it's going to stay there. But the real secret, the magic, isn't in what you can see. It's in the engineering marvel hidden deep beneath the surface. At its heart, a foundation is basically the ultimate middleman. It takes the colossal weight of a building, what we call the load, and carefully, strategically, spreads it out onto the ground in a way the earth can actually handle. That transfer of load, that's the whole game. But here's the thing. You can't just use a one-size-fits-all foundation. Nope. The design has to be perfectly matched to the building above and the ground below. So let's take a quick look at some of the most common types you'll find out there. Okay, first up, we've got the wall footing. Imagine a long concrete ribbon that runs continuously right under a major load-bearing wall. It's simple, it's super effective, and you'll find it under most houses. So if a long wall gets a long footing, what about a single column? Well, for that, engineers use what's called an isolated footing. It's pretty much what it sounds like. A single pad of concrete that's designed to take all the concentrated weight from just one column. But what happens when you have columns that are really close together, so close that their individual footings would overlap? Well, engineers just get clever. They merge them into what's called a combined footing. It's one single foundation that supports two or more columns. Problem solved. Now, sometimes you need to go even bigger. Let's say the soil is pretty weak or the building's load is just immense. That's when you might see a mat footing, also called a raft footing. It's basically one giant slab that the entire building sits on. It spreads the weight over the biggest possible area, kind of like a raft floating on water. And what if the soil at the surface is just bad, like too weak to hold anything? Well, engineers can just bypass it completely. They drive these long columns, called piles, deep into the earth until they hit solid rock or really strong soil. Then, a concrete pile cap sits on top of all those piles, funneling the building's load all the way down to that sturdy layer far below. So, everything we just looked at really falls into two main families. You've got your shallow foundations, those footings that sit pretty close to the surface, and then you have deep foundations, like those piles we just talked about. The choice all comes down to one question. How deep do you have to go to find ground that's strong enough for the job? Okay, so designing the concrete part of the foundation is one half of the battle. The other half, the really unpredictable half, is understanding the ground it sits on, and more importantly, all the ways that ground can fail. And that brings us to this absolutely critical concept, bearing capacity. Think of it as the soil's breaking point. It is the absolute maximum pressure the ground can take before it just gives up. The entire goal of foundation design is to make sure the building's pressure stays safely below this number. And when soil fails, it's not always a simple sinkhole. It can happen in a few different ways. For instance, sometimes you get a general shear failure, where the ground literally bulges up on the sides as it fails. Other times, it's a punching shear failure, where the foundation just punches straight down, like a fist through styrofoam. Let's break those down really quick. General shear, that's a sudden catastrophic collapse you see in dense, strong soils. Local shear is a little less dramatic. You get a lot of settling and a little bit of bulging, common in looser sand. And punching shear, that's what happens in really weak soil. The footing just sinks straight down, no drama, no bulging. So, knowing the types of foundations and all the ways soil can fail, how do engineers actually build something that is guaranteed to be safe? Well, it's all about methodically planning for the absolute worst-case scenario. You see, an engineer can't just design for a perfect sunny day. They have to account for everything that could possibly stress the building. You've got the building's own weight, the dead load. Then there's the live load, all the people, furniture, snow. And on top of that, you have to factor in extreme events, like hurricane-force winds or the incredible shaking from an earthquake. To figure out the soil's real strength, engineers often turn to a classic formula. And you can think of it like a recipe. It combines the soil's key ingredients, like cohesion, which is how sticky it is, and friction, how grainy it is, along with the foundation's shape and how deep it is, to cook up one final number, the ultimate bearing capacity. And this is it. This is the equation that does all that heavy lifting. Now, don't worry about the math itself. The important part is just seeing how all those ingredients from our recipe, the stickiness, the graininess, the depth, they all have a place in here. This formula turns those real-world properties into a single, predictable number. But, and this is so important, engineers never, ever design right up to that failure point. They always apply a factor of safety. A really common one is 3. That means the foundation is built to be 3 times stronger than the highest load it's ever expected to see. It is a massive safety buffer, just in case. Okay, time to put it all together. We've seen the pieces, we've gone through the theory. Now let's walk through how an engineer actually goes from a problem to a final buildable solution. You know, the process itself is incredibly logical. First, you calculate every possible load. Once you have that, you can figure out how big the footing needs to be. Then comes a really crucial check to make sure the footing itself won't crack. After that, you calculate the steel reinforcement needed. And finally, you put it all together in the blueprint. And that third step is so critical. See, it's not just about the soil failing. The concrete footing itself could fail. So engineers check for 2 major risks. One is beam shear, where the footing could snap like a board. And the other is punching shear, where the column could literally punch a hole right through the footing. So how do you fight those forces? With steel reinforcement, or as most people call it, rebar. Here's the deal with concrete. It's amazing at being squeezed. That's compression. But it's terrible at being pulled apart. That's tension. So the steel rebar is placed exactly where those tension forces are going to be, making the whole thing incredibly strong. And this is the final result. After all the theory, all the calculations, and all the safety techs, you get a detailed blueprint. This is the instruction manual that tells the construction crew exactly how to build the foundation that will safely hold that building up for decades. So the next time you're in a building, any building, just take a second to think about that complex, carefully designed hero sitting right there beneath your feet. It's an amazing reminder that some of the most important structures in our world are the ones we never even get to see. So, what invisible foundations are supporting you right now?